All right. Ooh, hey, it works. Cool. So, yeah, since this is the last session, I was tempted to be a little more entertaining and do some calisthenics and the like, but I think this thing is going to do that. So, we're gonna try to be a little more still than I normally would, but I can't help but doing a little walking. So, the title is What's New, and really, this title should have been called Trials and Tribulations of a PhD, because basically, for the past year, I've been attempting to get the dissertation written and make everything work and get the compiler to a point where academics would care about it, not just people who actually needed to get real work done. And that turns out to be significantly more difficult. But I looked back at what I'd accomplished and realized, well, it wasn't quite so bad. So I don't feel as bad now as I did before I wrote this talk. So that's good. That's good. And I also realized that we have a few people here who haven't had a Co-dfns update in a while. So I'm going to just do a quick overview of the basic features and what Co-dfns has done over the past few years first, and that's basically summarized here. And the end result of this is that we've got most of the Dyalog primitives. We have the defun support, guards, things like that. Recursion works. Error guards don't work. We run on the GPU. We have a built-in high-performance graphing API, which allows you to visualize your data on the GPU as well. We have a caching API, which allows you to offload data to the GPU before you do the actual computation, so that you can sort of manage your data transfer back and forth. We added an FFT support for people who wanted to do fast FFTs. It's multi-platform, so it works on the Mac, Windows, and Linux. And it also works on Intel CPUs, OpenCL CPUs, and CUDA machines. So if you have any of those platforms, it should run. It won't run at the same speed on all those platforms, but it does actually compute the results and you can use them. It has a C API as well, so that if you want to integrate APL computational code into an existing application outside of APL, then you can link directly in with the DLL through your C or C++ interfaces. And we're supporting most of the numeric data types that matter for high performance on GPUs for that you would see in Dyalog. So we've got things like ints, floats, stuff like that, and then we had Booleans. The big thing, though, is that this is all sort of before this year we had this kind of stuff. So what about over this year? And the name of the game for this year was largely get it correct to an academic standard, which is fun, but we do have some actual new usability features as well. So bracket indexing is now sort of fully supported, so you can use your semicolons, and you can get some of that going in there. That's a nice feature. I like that. You have a simplified installation. So now it has never been easier to get this thing up and running. You download and install the ArrayFire dependency. Make sure it's in your path. That's all taken care of in the installer. Then you copy your co-dfns.dialog file that you got off of the GitHub repository, put it into your user commands directory, done. Now you have access to the compiler. It should just work automatically for you. You do need to make sure you have a backend compiler installed, but I'm assuming that that was obvious. We supported namespaces. We don't do much with it, but now that actually comes in, so that's a usability thing. We've improved the primitive support, so a lot of the edge cases on some of the primitives are now better supported. They support more data types, things like that. We added our Domino, so Domino is finally in the Co-dfns compiler now, so you can do fast matrix divide, you can do fast matrix inverse, and there may be some limitations on the edge cases with really strange data types. But it's in there, it's doing stuff, and it should generally, it's expected to work. We also added some limited, but we do have complex number support in there now for certain primitives. They'll just work with the complex numbers, so you can do that. That's a nice, cool, fun little feature, good for demos. And parsing. So one of the big problems that I think Co-dfns delivers is it gives you a set of code that you can work with, study, and then use and reapply elsewhere. So one of the problems is it's difficult to do things with APL code because it's difficult to parse APL code. You have to do type inference on the APL code and doing all this other stuff. So the Co-dfns compiler provides one of the shortest, smallest, and easiest to understand parsers for APL. And that parser is now to a point where I feel that I can encourage you guys to play around with it and start using it and actually try to apply it to your code. It does only support the dfunds language, but adding in the tradfunds is not a particularly difficult task. And adding in things like strings, for instance, is also not a very difficult task. It is self-contained on 2 pages of code, and it uses peg parsing combinators, which is a well-understood technique. All of your traditional things that you might have learned about parsing applies, and you can see examples of how to deal with tricky situations inside of the parser. So for instance, if you needed to parse other stuff, if you have other kinds of data that you need to parse that's more complex than a regular expression can handle, then you can go look at the Co-dfns parser and see different techniques that you might use to parse more complex data in a clean way. It's still a little slow, but we're going to be eliminating that hopefully by the end of the year. It handles ambiguous parse trees, so you can parse all the ambiguous parts of the dfunds syntax and the APL syntax. And at this point, your first quiz. How many different ambiguous parsing options do you have for user-defined operators in the dfunds syntax? Go. I've got 1 and 42. Any other guesses? 42 is probably pretty close to the right answer, actually. Yes. I can't remember if it was below 30 or 70, but there was a lot. There's a lot of them. I think it's closer to like 30, but you get a ton of these. And so the parser will now parse those out and give you a different parse tree for each possible valid parsing of a dfunds for user-defined operators. And it does support user-defined operators in the system. It also supports indexed assignment and other things like that. It doesn't currently support selective assignment, but it does support bracket indexing. And it's gone through some code cleanups, so it's easier to read and understand. And in fact, the whole compiler has sort of gone through code cleanups, which we'll see. So really, when it comes to the parser, it's shakedown time. So anybody who's wanted to play around with manipulating trees, you can start by playing around with parsing your APL code. And if you have questions about that, feel free to ask me and I can give you demos. It's fairly straightforward. But I have had some questions about whether we can use this stuff in my commercial code. So the open source version of the compiler is AGPL licensed, and I know a lot of you won't like that. So instead, you have a Dyalog license that gives you free access to all of this stuff anyways. So as long as you have a Dyalog license, you're licensed to use the Co-dfns code. But if you don't have a Dyalog license, then you have to abide by the terms of the AGPL. And additionally, we've added some low-level stuff, so we get much better logging of array errors. So you have ArrayFire is our underlying dependency, and when we get errors on the GPU, which can happen and they're really nasty, we give you better logging and better information all across the board on that, including things like if you've got version mismatches, stuff like that. And I love this. You no longer have to do any workspace magic to get the compiler to work. All you have to do is drop your Co-dfns file into your user commands directory, and it works. So there's a user command, a Co-dfns user command that will allow you to take a scripted namespace, and I think even an unscripted namespace, and just give it that name, and then the name of the compiled object that you want it to be bound to, the name of that a variable name, and from there, it'll compile it for you, and then you will have your compiled namespace ready to go right at the session without having to copy in any Co-dfns pieces or anything like that. You just go from there. And as part of that, the files will build in whatever is your current working directory. So we took out some of the configuration options so that it's much more predictable and you don't have to worry about configuring that path when you're working with the Co-dfns user command. It also does compiler auto detection. So previously, some of you will have gone to the Co-dfns workshop and will recall that they had trouble getting their version of Visual Studio to work. That should no longer be a problem. You simply go, and it will detect what version of Visual Studio you have installed on your system and simply use the right version. It also will automatically select the backend for you, so you don't have to depend on knowing which backend you want to use. You can just select the unified backend, and it will try to auto-guess whatever backend they want to use. So it'll try to go with CUDA first, and if it can't find that, it'll try OpenCL, and if it can't find that, it'll fall back to the Intel sort of fallback layer. And we also improved the performance of the plotting widget in the compiler, which I really don't want to say that the compiler has a plotting widget, but because traditionally none of the other solutions have been fast and easy enough to get working, there are graphing and plotting things inside of the compiler. So we've improved the performance of plot in that case. We also have a nice thing for compile time. So previously, the compiler would just insert all of the runtime into your code as a part. Now, it detects what primitives and what features of the language you're using and only includes the runtime code that's necessary in order to compile those features. So it should result in reduced DLL sizes, for instance. We've improved the GCC compatibility, so it should work on a wider variety of Linux implementations. And this is where we begin to get into the headache. Is previously I was assuming that you would just write single assignment defunds code. Most people don't write single assignments defunds code. Sigh. So I had to support duplicate bindings, and therein lies a lot of work, which we'll get into. But to clean up sort of the rest of the features, you know, binomial and other things have been cleaned up. We've done some cleanup around the edges, so things like empty defunds return the right values now. All that kind of stuff, bug fixes, things, that's all good. Lexical binding is the pain. Lexical binding in defunds, I've been spending a lot of time trying to make sure that this is actually correct and that it has the right behaviors and correct runtime performance and things like this. I needed it to run fast, and I needed to deal with defunds dynamic behavior. So, quiz number 2. What does this evaluate to? I know this is a tough one. Come on, guys. 5, yes. Excellent. What does this evaluate to? Ding, ding, ding. Yes. So now you'll notice here that we're using a duplicate binding name, right? So one of the x's refers to that x bound to 6, and 2 of them refer to the x gets 5, right? And there are different ways of handling this, but what this basically means is that defunds overloads the get operation so that it is both a binding introduction or a definition form as well as a mutation form. So in Scheme, for instance, you have let and setbang to separate these out. In defunds, they're the same thing. So what about this one? Zero, of course. Need you even ask? So you can sort of see we're doing sort of a 5 iteration over 2 times on 4 plus iota 5. So you've got 4, 5, and so forth, up to, I think, that's 8. And so you get something like this. But what's important here is that the x that you pass to f is that array, but the x that f gets is the 5, right? So that's showing that the operators are early bindings, right? So far, so good, right? Easy. What does this give? So we have x gets 5, the function that takes its left argument and its right argument, adds it to x. G is x bound with f, and then we get x gets 4 and call G on 3. People write lots of code like this. So what's the answer here? 12. This is critically important here. F does not resolve the reference to X until call time. Another way of saying that is you could treat all of bindings as parameters or set-banged mutable objects that get changed. So a defns only introduces one lexical scope or one lexical contour within its body. That means that all the bindings to X essentially refer to the same theoretical cell, so changes to X have to be reflected to any reference to X inside of nested functions that have free variables referring to X. Easy, right? Another way of thinking about this is basically they're lexically scoped but dynamic. Here's another example. So here, we only have one X in the outer contour, right? So we're good there. But we have actually two different X references inside of the inner function. So even though we have bound X inside of the lexical scope of F, we also have two references to X that are considered free, but one reference to X that's considered bound. So we've got to be able to handle that somehow. So that's 30. Now we get even more fun. So here we have an early binding of X to F, but we have a late-ish binding to Y inside of O, but then we have another Y that we introduce inside of F before we call O, and that's also referring to an X inside of there. And then we have an X and a Y bound at the tail end before we call F. Style error. Well, you know. So now if you work this out, what we have is we have that Y there is actually a red herring, right? Because we are lexically scoped, which means that the reference to Y inside of that O function cannot possibly access anything inside of its neighboring lexical contours. It can only look up the lexical stack, if you will, right? So it has to refer to that one over on the other side. And because there's an F binding there, that compose operator, that X has to go to the first one. That has to go to the 5. But when we call F, there's also another reference to X inside of F, and that one has to refer to the one over on the right. Anybody thinking of a good formal semantics for this yet? So this is basically the story of my life for a significant portion of this year, because I needed a good solution to this on the GPU, and I've come up with a novel solution, but I needed it to preserve single assignment because I needed it to perform quickly, right? And so the solution to this does so without actually ever using cells. So the traditional solution to this in any other language would be just treat all of these variables as mutable variables. So every X creates a cell or a box or something, and we set bang it, if we use the scheme terminology, down the line, and it would work fine. That's a fairly easy transformation to do. The problem there is that it completely eliminates your ability to do more code optimizations, right? And one of the benefits of having a single assignment is you can do all these code optimizations. So the solution that I've put together allows you to avoid any new cell creation. It's all native basically. You don't have to rebind anything, but you still make sure that you handle that mutable variable case. And the way we do that is we don't create closures at definition time. Instead, we create closures at call time. And we have to do the analysis to make sure that each of those closures handles all the free variable captures, because we have free variable references up, but then if we have a free variable reference to a function that itself has free variable references, we can also have propagation out and across. So it's like a 2- or 3-dimensional variable reference propagation problem. And we have to make sure that works, and we have to do so with good performance. And that means we need to avoid complex algorithms. It needs to be simple, it needs to be vectorizable, and it has to be Mantis 17 approved, which it is. You'll be glad to know. My one tiny victory against the army that is the Dyalog programmers is I think that I managed to get the Mantis 17 bug, you know, I was inoculated to it from the start, so I was happy about that. But we also have to make sure that the recursion handles things and all of this. So We got to handle global variables. That's an important piece. So this actually meant that now with this new analysis, the global variables are handled in a better way. So previous versions of the co-dfns didn't expose global variables in a way that you could access them. Now, even though it's not in the namespace that we give you, because I don't want you to change those variables, if you need to get access to the global variables inside of your compiled namespace, you can get access to them now. And there's an API for doing that, a consistent naming convention and so forth. So they are now exported, which is a new feature that's kind of nice. Additionally, there's less overhead because the compiler underwent a rewrite to improve the asymptotic and constant factors around the whole system. So this is a big one that's pretty important. And additionally, we provide some more feedback when you compile stuff, and infrastructure is all in place now for first-class procedures. So they're not in yet, but if Dyalog ever decides to take a crazy plunge into having closures as a first-class procedure type thing, I'm ready for them. I also have all the prep in place for sparse matrices, so there's plans in place to add the sparse matrices support. User-defined operators, the parser's ready, the backend runtime is now ready, so all we need to do is handle the intermediate pieces inside the compiler. A lot of bug fixes went in to ensure that everything was working correctly. We now also the compiler is designed so that it can actually compile multiple namespaces simultaneously. So you're not restricted to compiling a single namespace. The parser in the system won't let you do that yet, but there's nothing inherently preventing you from using the compiler to do that now. The algorithms will handle an arbitrary number of namespaces compiled all at once. And this actually means that we can fairly easily extend it to handle free references across namespaces that are compiled together. So now we have cross-module references that we can do. And we've made the compiler significantly easier to read and maintain. So let me see if I can pull this up here really quickly. Well, is it going to go? Yes, go. Go, go. All right, keyboard time. So, where did it go? Yeah. There we go. So on the left is what the compiler used to look like. And on the right is what it looks like now. So I won't give you too much time on that, but it is significantly easier. And now it's not doing anything that's too crazy like we were doing before with some of the trains. It's one single defns. So I like that. That's not too bad. Additionally, there's a tree pretty printer called pptree. So pretty print the tree. And everybody's got to have a pun in this group, right? So that will allow you to pretty print trees, and that's a useful utility both when you're working with trees the way I am, but also if you want to debug the compiler, or if you want to write your own tree code and visualize it, you can do that. And so in short, the whole year has been about smaller, corrector, and betterer, basically, across the board. So now the compiler is 40 lines of code versus 90 in the previous case. It's probably going to bump up to maybe 60 or 70 by the end of it, but we've shrunk it quite a bit and simplified things. The compiler now we expect to be linear memory, log linear time, and log critical path for its performance, which I think is pretty good. And if you would like to see more about how you can do this to your own code, particularly if you want to see how to do trees in the way that we're doing it in the compiler so that it's fast, works on the GPU, and scales to all sorts of stuff, and works the APL way, that's my tree talk on Thursday. So I'm going to discuss and show how all that works. So thank you.